All right, so the problems that I gave you were the ones that you actually could use the little trick that I showed you when you're involved with the electrostatic force, the electric field intensity, the voltage, and the work. When any of those are involved, then you can actually use that little trick that creates the formula that's relevant to the problem you're solving. So in this particular problem, if I look at it, I see that it says a particle with a charge of negative 2 microcoulombs and a mass of 3.4 times 10 to the 6 kilograms is released from rest at point X and accelerates towards Y, arriving there with a speed of 72. What's the potential difference between X and Y? So potential difference, that's the V, and anytime they give you a charge, that's going to be your test charge. That's going to be the QO, because Q is always there. If you look at the formula for electrostatic force, for electric field intensity, for voltage, and for work, the source charge is in all of them. What makes one different than the other is not all of them have the test charge. So in this one, we're given the test charge, and we're given enough information to get the work, because they're telling us that the charge starts at rest and then reaches a speed later on. So the kinetic energy is changing. So if the kinetic energy is changing, then it's changing because work is being done. And that's one of the big four. The big four, again, being F, E, V, and W. So what I'm going to do first here is I'm going to solve for the work. So the work is going to equal the change in the kinetic energy. And the change in the kinetic energy is the final kinetic energy minus the original kinetic energy. And the original kinetic energy is 0 because the charge starts from rest. So if I can figure out the final kinetic energy, I'll know the work. So the formula for that is 1/2 mv final squared. So we're going to have 1/2. The mass in the problem is 3.4 times 10 to the negative 6 kilograms. And then the final velocity is 72 meters per second. So we have 72 meters per second squared. And if you solve that, what does that give you for the work? What does that work out to be? Bless you. While you're figuring that out, the charge when it says negative 2 microcoulombs. In a problem like this, it doesn't really matter. I mean, the negative means when they say a potential difference between X and Y, it would mean like whether it's going from the positive to the negative terminal or the negative to the positive terminal. So it doesn't really, it's not really that important. I don't really even have to put it in my formula because the negative, again, it's just telling me whether it's going from positive to negative or negative to positive. All right, so what do you get? 8.81 times 10 to the negative 3, and that would be joules, because work is measured in joules. Okay, so we have the work. Now the charge, so that, like I told you, that's going to be the test charge. So you have QO, and the test charge is negative 2 microcoulombs. Now, microcoulomb, most of the charges that we deal with are of the order of microcoulombs, because that's sort of the size charge when we're doing these problems. So, but we need that to be in coulombs. So I'm going to write that as, in fact, I'm not even going to put the negative in because it doesn't really matter here when I'm solving. I'm looking for the potential difference, so I'm just going to write it as 2 times 10 to the negative 6 coulombs. So 2 microcoulombs is equal to 2 times 10 to the negative 6 coulombs. So I have that, and the unknown in the problem is V. So V is in volts. Now, a volt is a joule per coulomb. So without even doing the little trick that I showed you to create the equation, if you look here, that's in joules and that's in coulombs. So I pretty much can figure out that I'm going to take that number and divide by that to get that answer. But I will, just to show you the process where you're creating the equation, let's do that, because in other problems it might not be that easy. So So what I'm going to do is I'm going to write my V and my W. Those are two of the big four. Again, remember the four are F, E, V, and W. So V and W. V is KQ over R. W is KQ QO over R. So I'm going to need, in order to make these two equal, I need to multiply this side by QO. And remember, there's a couple of ways I can do it. I can either multiply this side by QO and then they'll be equal, or I could divide this side by QO. If I have a choice, I'm going to usually multiply because I'd rather not create a fraction up here. So I'm going to multiply by QO, and whatever I do here, then I'm doing up here. Because remember, this represents V. So if I'm multiplying that by QO, then I need to represent this as being equal to what I have down here. Now they're equal. So if they're equal, so if they're equal, then now I have an equation that compares V to W. And my unknown in the problem is V. So now I'm going to take this equation and solve it for V. So actually now I'm actually going to bring it down there where I suppose if I knew ahead of time that V was the unknown, I would have just adjusted this side and then I wouldn't have to do this next step. So solving for V, I'm going to get V equals W divided by QO. So the W is 8.81 times 10 to the negative 3 joules, and that's going to be divided by 2 times 10 to the negative 6 coulombs. And so if you work that out, what do you get? What's the number I gave you? 4.41 times 10 to the third. Okay, so 4.41 times 10 to the third, and that's a joule per coulomb, and a joule per coulomb is a volt. So that's the work in solving a problem like this. All right, any questions on that one? Again, I could have saved myself a little bit of time. No, like I told you, a lot of times with these problems, I don't even necessarily have to know what these formulas are. If I know the units that my answer has to come up with, and I've got facts that produce that, that's probably what's going to happen. So in this problem, I could tell before I even did this stuff over here, I could tell that, well, that's joules, and that's coulombs, and a volt is a joule per coulomb. So I sort of knew what I was going to have to do before I did all this stuff over here.